I am excited to introduce our next talk here. There are 4 speakers for this one. Coming to us from Target, we've got, and if I butcher anyone's name, I apologize to him. I'm going to try my best to get these right. Fred Nolte, Nikita, Jain, Dante, Razo, and Jacob Alongi, who are going to be joining us from Target and talking to us about leveraging beacon detection techniques to identify anomalous logons. Now, I'm going to tell you right now, nearly every single word in this title caught my interest when I first read through this particular CFP, primarily because this is something that I feel as an incident responder, as someone who's crafted detections, as someone who's done some work in this space before, this is one of the hardest things to do. Simply detecting malicious, if you will, logins or anomalous logins, maybe more appropriately classified, is not the easiest thing to do whatsoever. And I'm happy that this team is here to present this with us. The other thing that I will make a mention of before I hand it over to this team, this is an area where a lot of attackers focus their energy, is how to avoid detection. So the more tips and tricks we have to detect them, the better off we're going to be. So with that, Fred, I think you're going to start the team off, so I'll hand it over to you.
Awesome. Thank you very much, Matt. Hopefully everybody can hear me all right. Great introduction. So thank you to Matt. Hello, everybody. We are the team from Target. As Matt said, we're going to be talking to you today about how we leverage some beacon detection techniques in order to identify anomalous logins. So first off, as you've seen elsewhere today, brief introduction to the team. So my name's Fred. I've been working with Target for about just over 4 years. I originally started out on the CSERT team after a brief stint as a software developer. And then I joined the threat hunting team last October.
Hi, everyone. My name is Nikita. I joined Target's incident response team, or their CSERT team, back in February as an intern. Decided to join full-time in August.
Hi, everyone. I'm Dante, and I'm an intern on the incident response team.
Hi, I'm Jacob, and I'm also an intern on the incident response team.
So yes, we do have 4 speakers here, and that is because partially due to just how we hunt at Target. So we do regular hunts that combine our threat hunting team along with our incident response team. So each one of these guys I have with me today definitely used their expertise and contributed a major portion to what became this talk. And realistically, the more smart people you have working at a problem, the better hunts you're going to get. So for us at Target, we hunt a specific topic weekly or bi-weekly since COVID happened, unfortunately. And we kind of break up our hunts into different use cases. So we kind of roughly define a use case as a discrete analysis approach taken during the hunt. It can also kind of show up, we might split a use case on different data sets. So for instance, for logins, 4625 failures versus 4648 failures, stuff like that. And really, so this talk is going to be a more technical talk than what we've seen today, just covering one of the more interesting use cases for a hunt that we did on password spraying. So I'm going to walk you through the background and kind of how we arrived at this methodology. Dante and Jacob are going to walk you through some of our analysis methods and visualizations, and we will talk about code, but we're going to distill it down so it should be nice and easy for everyone to process. And then Nikita is going to take you through some of the validation efforts that she took to make sure our analysis methods were really correct and kind of on point and would actually help identifying a password spray. So just a brief basic introduction to make sure everyone's working from the same foothold here. So a password spray differs from a brute force attack. A brute force attack is going to be many different passwords tried against one account, whereas a password spray might look something like this. So you're going to try a few common passwords against many accounts. So if an attacker is going to try and spray Dante, Fred, Jacob, and Nikita, they might try the password like summer 2020 and spray against all 4 of us. And then they're going to switch passwords and spray against all 4 of us again, and keep going until they hopefully compromise an account. So what we've found is that usually for like the baseline level attacker that just writes a couple for loops up and scripts this out, it's going to be identifiable by volume. So if you see a graph like this in your login failure events, hopefully you're going to go look at the spike and go investigate that. This graph isn't actually related. It just shows our point really well. But yeah, so these are normally detectable by volume. And obviously attackers know this. So they're going to take some steps to prevent this. So for an advanced password spray, so they might start with something, like I said, just a couple of for loops. So for each password they want to try, for each user they want to try that password against, try and log in with that user and password. An advanced attacker might do something like this. They might only try their login during normal working hours. So for target's case, that's like between 8 and 5 Central Time. And an attacker might also implement a sleep timer. And they might say, okay, we'll log in. We're only going to try to log in every 30 minutes or something. And this is kind of what got us thinking. So attackers are going to use the same techniques that they use in obscuring their C2 beaconing to potentially obscure their password sprays, right? So smart attackers are going to know that there's intervals in how their scripts are running, and they're going to try and obscure those intervals. So this led us to our ultimate question that kind of spawned this use case and this talk. Can we detect automated authentication attempts by their regularity?
All right. So our data contains roughly 50,000 failed login events over the span of 2 weeks. The larger your time frame, the bigger your chances of finding password spraying. So any login event type would have sufficed, but we chose 4625 events because they're easy to understand. These events are the generic Windows login failure events. Different methods of password spraying might generate different event codes, so it'd be worth checking out the other types of events as well. And here's a preview of what our data looked like at the very beginning of the process. So each row is a login event that contains a timestamp and an associated user for that event. So this is a visualization of the dataset that we made using Python. This plot has users on the y-axis and dates on the x-axis. To generate this graph, we sorted users by order of first occurrence. So we can see user 1 at the bottom left because they had the earliest event in our dataset. The reason this graph looks like a ramp is because of that sorting method. As time passes, more and more unique users will have login failure events. The green box is an example of normal working hours, which appears thick vertical bands in the plot, and we consider this normal activity. Events are sparse on the weekends because less users are trying to log in. You can see this in the purple box, which covers the weekend of August 8th and 9th. And at the very bottom of this plot, I highlighted a segment of user 1's activity in orange. Solid horizontal lines like these are caused by users continuously failing to log in. So now consider the rest of user 1's activity beyond the orange box. It's a continuous line from the end of July to mid-August. This definitely is a normal login activity and could be indicative of password spraying.
Data visualizations. So first off, why do we want to visualize the data? When we started doing this as an intern, I didn't know much about this project. So we really just did it to understand what was going on quickly. We were trying to find mismatched data. We were trying to reduce noise in our results and see if we could actually just visually detect the password spray. So this graph is the top 100 users for the most login fails. And on the x-axis, we have the date that the failed login occurred, going back 15 days. And on the y-axis, we have a count of failed logins. And if you notice, the blue user has just under 8,000 failed logins, which just has to be automated. But also, most of the users have a little bit less than 1,000 failed logins over 15 days, which is still huge. I don't know anyone who logs in and fails more than a few times over 15 days. So all of this we can chalk up to say is automated. So let's try to find what we assume is a password spray attack when the graph is visualized this way. So look at this user. We have an unhuman amount of logins over 33 hours, but it has some things we're looking for. We're looking for high density. And essentially, each time someone fails a login, it's plotted on there, but it's so dense, it looks like a straight line. And so we're looking for that straight line, and we're looking for a high slope. We're also looking for straight lines because we'd expect an automated login attempt to have very consistent intervals between failures. And we're also looking for gaps because we're expecting some cycled automated activity. So this data kind of looks good, right? It looks like a password spray. But the answer is it's wrong. And the reason why is because we're looking for multiple users with similar clusters. As you can see, blue here just completely mismatches the rest of the data. It's nothing similar. It skyrockets in volume, and there's just no consistency. Red is also kind of a mismatch fit. But as we're looking at the data here, you can start to see green and yellow down there are looking a little bit promising. But the data is just way too compressed. And if this is a password spray, we would see this pattern with multiple users. So let's look at more users and start filtering the data. So this is now the top 100 users, but the top 2 are obvious outliers. And as we'd expect, we'd have a noise floor and some outliers that we want to get rid of. But the rest of the data still looks kind of promising. So now we're just trying to remove outliers and unsquish the data. So now we have the top 50 users with the top 3 removed. And there's still some outliers here. Blue doesn't match, obviously. It's a way higher volume, and it's not very consistent. And red also is an outlier because it just has this massive, in the center there, volume of failed logins, and then nothing after that, really. But you might be able to detect something that looks what we're looking for here in this. So do you think you could spot what looks like a potential password spray attack? And again, if you look for similar slopes and clusters, you'll see that these several of these clusters are looking very promising. We have this parallel line to each other with these dense clusters that have these look like cyclical login situations. And so they're all similar. And it's great because they have similar slopes and clusters. So after doing this, we thought we had a really good understanding and a method to visually validate password spray attacks and what erroneous data might appear to throw out.
So we calculated metrics on time deltas, which are the lengths between consecutive login events. Our code works by first getting a list of users and their events, then sorting them in chronological order. At this stage, our data looks the same. We still have a column of event timestamps and a column with the associated user. And in this case, that's user 5. Next, we calculate deltas for that user. Once we get those, we add a new column called delta, and the data looks like the table on the bottom right. This delta column is what we generate statistics on. So for each user, we calculated a handful of useful metrics that helped us identify cases of interest. The first of these is the mean, or the average. We find similar means among users interesting because it's indicative of automated login attempts. And in a similar vein, login failures per minute is a metric that tells us how dense a user's login activity is. There's a lot of activity in a short time frame that could imply password spraying as well. So another stat that we made use of is the standard deviation. You can think of this as a measure of how regular a user's login attempts are. On these lines, we represented the login activity of 2 separate users as black dots. So the first line displays expected password spraying behavior. The events are regularly spaced, so the standard deviation will be low. The second line will have a higher standard deviation though, because the events are irregular. So low standard deviation implies very regular events. For this reason, we sought users with lower standard deviations as potential victims of password spraying. And this is why attackers might implement jitter into their scripts. It increases standard deviation and makes password spraying less detectable as a result.
So in order to validate our hypothesis, we decided to fake a password spray for 15 randomly chosen user accounts. We did this by seeding the data and inserting fake events. We spaced each of these events 5 minutes apart and made sure that each login attempt had a 5% chance of failure. This was to add additional variance into our data, as well as making sure to simulate potential errors that attackers might run into, such as network errors. So if you look here, we graphed our data here, and we decided to graph the top 50 users. And what you can see here, it's pretty evident where the password spray occurred. Now let's zoom in to that password spray and let's see what we can take a look here. So if you look back to the definition of a password spray, what it is basically the attacker will be trying various passwords, and for each of these passwords, he's going to be trying the same password across multiple different users. So in each of these boxes here, you can see sort of similar activity, which occurs between the different passwords. You can assume that each of these boxes is sort of, one password that's being tried across different users. You can see how similar these boxes are in terms of their shape. It's almost like a sine wave that's kind of repeating its pattern over and over again. This just screams automation to us. This consistency sort of ties back into beacon detection, because one way to look for that is to look for C2 callbacks and how regular those are. So that sort of mirrors it within our data here. We decided to look at the statistics of the spray that we simulated. And here you can see the count, the mean, the standard deviation, and the average logins per minute of each of these users. These 4 users were randomly chosen from the 15 that we sprayed. There's no particular significance to them. What we can see here is that the mean and the standard deviation were not as great indicators of a password spray. There doesn't seem to be any sort of similarity or any number that they sort of center around. We chalk this up to existing password failures from these very real users within our data set. On the other hand, the count and the average logins per minute seem to be fairly steady. The count, as you can see, was roughly 170 attempts, and the average logins per minute was around 0.01, which averages around to 1 failed login per 100 minutes. So that seemed to be a pretty good indicator of failed login attempts. So here we decided to implement a more advanced password spraying technique. We did this by implementing jitter into our password seeding, into our data seeding. We did this by spacing the events randomly plus or minus 2 minutes based from each of the 5 minutes apart that we had earlier. We did this only during target's working hours, so that would be between 8:30 a.m. and 4:30 p.m. and we decided to not spray on the weekends. Once we graphed this out, it was pretty hidden. We weren't able to immediately see where the password spraying was, but so we're just looking at the top 50 users right now, but the magic happened when we singled it out to the top 30 users. And you can see here in these boxes that the password spraying was pretty evident here. You can see there was a very steady stream and a very very linear attempt of password logins across these different users around the same time and also the same rate.
All right, so further advancements that we could potentially make. So obviously, we know that visualizations were great, but we really expected our stats to be better. And really that's because of 2 things. So one, we have those outliers that we already know about. So those really high count users on the graphs. Or the obvious, like, okay, where someone's failing logins like 1,000 times in 2 minutes or something like that. Automating those outliers is a good step to kind of improve stats. Additionally, we would like to remove gaps in user login activity. And what I mean by that is illustrated by this user that Jacob talked through earlier. So realistically, we have a 14-hour gap between the last event in their first string of login failures, so that first line here. And then the second box, so there's that 14-hour gap between the first event in the second box and the last event in the first box. And if we found a way to either split these up into 2 separate like users, you can think of them almost, then our stats are all of a sudden going to get a lot more consistent, right? So this is what Dante and Nikita and Jacob alluded to with our stats kind of getting bloated because of real login activity being interspersed with our password spray. And then really, so for us, like I as the hunter definitely took a ton away from this. So the first thing for detecting password sprays, the volume is still surprisingly good. So like Nikita said, we faked our spray on weekdays for, I think it was about 5 or 7 days over a 15-day span of time. And all of our users that we chose to spray against, even with the 5% chance of like just not having an event pop up, they all still showed up in the top 30 users. So it's totally still viable to grab like your top 50 or 60 users by just login failure counts and vet each one of them individually. It's just a little more annoying than the method we took. The second thing to take away from this talk is that obviously visualizations were really key here. Our stats didn't really line up in how we wanted it, but we understand because of the visualizations why they don't line up. We also understand what outliers kind of due to the data, and they really help us find those interesting patterns that led us to being able to detect password spraying using this method. And then last thing, especially for me, trying new analysis methods and cross-pollination, I like to call it. So looking at other hunts or other topics or other analyses that you've done in the past and trying to see what might fit here, right? It was really that key moment when we realized, oh, attackers are going to use the same methods to obscure their password spray scripts as they might for a C2 script. So that was a key moment here, and looking for more opportunities to do that, I think will greatly improve hunts in the future. So thank you everybody for listening to our talk. A special thank you to Stans as well for letting us present. And for Target, I don't know of any interns that have presented at a cybersecurity conference during their tenure at the internship. So that was super cool of Target for giving them the opportunity to do that.